In this segment, we'll take our first look at that built-in type classes and their instances. Here's a diagram from the wiki book about Haskell that tries to cram in all the type classes. Now, I'm going to omit some because they're not really central to what I want to talk about in this course. They're ones to do with fractional numbers. And I'm going to postpone talking about some others until another segment in a couple of weeks' time. So what I want to do here is talk about these, which cover some of the basic classes like EQ, show, read, ord, things that we've seen already, and some of the numeric type classes and how they're interrelated. So that's the diagram. Let's get started with looking at what we can find in the built-in type classes. Something that we've seen a lot is the EQ type class for equality. It's described by the interface that contains two functions. One is the equals function, the other is the not equals function. They're both of type A to bool, so they compare two elements of the same type, and for A to be in that class, at least one of those has to be implemented. And you see what's called a pragma here, the final line of the text on the right hand side. It's signaled by the squiggly bracket minus hash parenthesization, and that says a minimal implementation is either equals or not equals. And in fact, I talked earlier about how there was a default implementation of each in terms of the other. The other thing to say is that this information is given by typing :info EQ to the GHCI prompt. Let's just take a look at that, because it doesn't only give us that information, but it gives us information about all the instances, or all the instances among the built-in types. So if we type info EQ, we get screenfuls of information, but let's scroll back to the beginning. What we get is we get the definition of the class, EQ of A, and it tells us about the two functions that are in the interface in the class declaration, and gives minimal, and then it gives us a whole lot of instances. It says integer is a instance of EQ. If EQA, if A and B are instances, then either AB is an instance. If A is an instance, then maybe of A is an instance, and so on and so forth. So and towards the end of the listing, it mentions that bool, char, double, float, int, and lists and so on are all instances of EQ. So pretty much everything is an instance of EQ except function types and IO, some of the monads to do with input output. So most things have EQ instances, but not all. So ordering the class ord extends the class EQ, and you can see this in the declaration on the right, which says if A is an EQ type, then you can define an ord type if you provide the functions here. And there's a lot of comparison functions: less than or equal to, greater than or equal to, maximum, minimum, and a function compare. And we can see on the left hand side a definition of how compare works. It returns one of the three values LT, EQ, or GT according to how the first and the second arguments of compare, as it were. So that gives us the three possible outcomes in a single function call. Whereas if we want to know that just using the binary operators, less than or equal to, and so on, we need to make two comparisons, or we need to make an explicit equality comparison. This gives us the three options in a single go. And you can see again, in terms of minimality, it's enough either to implement compare or to implement less than or equals, because you can see on the left, I've implemented compare using less than or equals and equals, which we can also use because ORD inherits from EQ. And obviously it's easy to say when something is less than or equal using compare, you say that when you apply compare, the answer is not greater than. The answer is less than or equal, i.e. not greater than. So there we have the ordering. And again, if you look at info ORD in GHCI, you will see that there's a whole lot of instances of ordering. Okay. We also have types which we can think of as coming from an enumeration. We can lay them out one at a time, x0, x1, x2, and so on and so forth, like the positive integers. And you can imagine that every number has a successor, every number has a predecessor, or maybe not every number. And the minimal instance are the functions to enum and from enum that convert between the enumeration and integers. Now, they can be derived for real enumerated types like bool and compare, but they can be implemented for many other types. And you can imagine it's not terribly difficult to think about how you might want to implement them. There's another rather more minimal class called bounded. And that simply has two values attached to it. It says there are upper and lower bounds on the values in this type. There is a minimum and there is a maximum. And the minimal implementation is that you have to provide both of those. Now it's fine, it's obvious what the minimum and maximum are for a finite type, but also for int, there is minint and maxint, because int are fixed size integers. These are not integer, the type which contains all the integers. Int is bounded, and so there is indeed a minimum and maximum integer and character. So bounded provides, if a type is in the class bounded, then there are two values identified, min bound and max bound. Okay, we've seen this class quite a few times already, but let's talk about it a bit more formally. The class show embodies the function that takes a value and turns it into a string. So that makes a value visible, as it were. We can then print the value out as a result in GHCI, for example. Now, most types belong in show. Built-in types come with show functions. For data types, it's possible for many cases to derive an implementation of show that prints the data type as it appears, that a value being a constructor applied to one or more arguments. And indeed, most types, apart from function types and IO, can be printed. Now, of course, we can, if we wish, define our own instance for an algebraic type. And for example, for expressions, the derived version of the show would print the expression as constructor applied to some arguments. We could use the print function, which we defined for expressions, to turn the expression into a string that looks much more like the mathematical expression. So sometimes there are good reasons for a data type not to use the derived version, but it's helpful if all we want to do is print something out as it appears in the constructor form, then to have that derived automatically. Now, the converse of printing something out is to read a value in from a string. So to turn a string into a value. And the key function here is the read function. It takes a string and extracts a value of a particular type. Now, it doesn't know that there are different reads for different types, and the only way you can tell which read to apply is not by what it's applied to, but by what results we expect. So when we call read, we're going to have to say, give me back something of a particular type. So if we say read from the string space 1234 space an integer, we get the integer 1234. You can see read strips off white space from the beginning of the string. In a similar way, we can read a string from a string. Remember, the strings are represented in Haskell between double quotes. So we have two quoted double quotes inside our string, and we extract the string hello from there. But of course, it may not be possible to extract something. So if we try and read a string from just the simple string hello, it's not possible. We get the exception no pars. And similarly, if we try to read an integer from that same string, we get that. So this, as you can see, is a parsing function, like the parsing function we defined for expressions. Now, it's possible to derive parsing functions in some cases, and that can be helpful if we don't want to do something like that ourselves. But typically, parsing is an operation we want to define for ourselves, perhaps for efficiency reasons, perhaps because of the peculiarities of the representation from which we want to read. So typically, we define our own instances of read, or we just define parsers for ourselves. So it's not these are not functions I use terribly often, whereas show functions we use all the time. Now let's move on to the numeric classes. There is a class num that contains ints of fixed and arbitrary size, floating point numbers, double size floats, and words, which are words made of bits. And on these we can do plus, minus, multiplication. We can turn a value to its negation. We can take its absolute value, that is, lose the minus sign if there is one. And signum gives us 1 if the function is positive, a number is positive, 0 if it's 0, and -1 if it's negative. And there is a class of minimal functions that need to be implemented there. As you can imagine, you don't need both negate and binary minus. Each can be defined in terms of the other. So those are the simplest class of numbers. But there is a rather narrow extension of that, of what are called real numbers. And this is confusing because ints are not real, really, which adds this one extra function, which takes a number to a rational. We won't talk anything more about rationals in this course, but it also requires an ordering on the numbers. You can see in fact on num, there was no requirement for there to be any ordering on the numbers. When we turn that to real, we ask for real inherits from, real extends num a and ord a. So it has the functions from num a and the functions from ord a, plus this 2 rational. So now looking at integral whole numbers, we require those to be in num and ord. We get that from real, and being in enum. And if they extend all those interfaces, if they're instances of all those classes, then we also include quotient, remainder, div, mod, things for doing whole number division, and quotient, remainder, div, mod, and a conversion function that takes something of this type to a integer. Now there are other classes, fractional, real frac, floating, and real float, which I'm not going to talk about, but you can see the documentation for those, or you can get information about them by typing :info and the name of the class. But that covers all the numbers that I would like to talk about in this introduction. So we have integral, that gives us all the division functions. We have num, which gives us the other arithmetical functions.